Hello, everyone. My name is Sahil Dua, as Phil already introduced, and I work at Booking.com. And today, I'm going to talk about a very unique combination of deep learning, which is a special branch of machine learning, and containers, something that all the cool kids have been talking about these days. So in short, this talk is going to be about how we productionize our deep learning models, how we deploy them using containers and Kubernetes. I hope I covered all the buzzwords. So let's start. So before I start, I would like to talk about the agenda. But before that, can you please raise hands, those who have used deep learning? Those who know about deep learning, what deep learning is? OK, quite a lot. And now, those who have written apps which run in containers. OK. OK, cool. So I will start with discussing some of the applications of deep learning at Booking.com, which were really unique to us, and how we solved them. Next, we're going to talk about the life cycle of a model. What are the different phases in the life of a model from the idea stage to the production. And next, I'm going to talk about our deep learning pipeline, which contains all the buzzwords that I mentioned. So before that, who am I? I'm Sahil Dua. I'm a backend developer building deep learning infrastructure at Booking.com. I'm a machine learning enthusiast, which means I spend a lot of time in learning about different technologies, different new things coming up in this industry. I'm also an open source contributor, and I've contributed to a bunch of projects like Git. Probably you use that in your daily life. Pandas library, which is a library for data analysis written in Python, and a bunch of other projects by Google, Mozilla, and a lot of other organizations. And I'm a tech speaker, and that's why I'm here on the stage today. Let's start. Let's start with the applications of deep learning. Before that, let's talk about the scale. Why are our problems interesting or hard to solve? We have more than 1.5 million room nights booked every 24 hours across more than 1.4 million properties in 220 countries. So I'm not here to brag about these numbers. My only point is that we work at a huge scale, and that provides us huge amount of data that we can then utilize to improve the customer experience further. So the first application that we saw was image tagging. So when we see this image, the question that raises is, what do we see in this image? What is there in this image? While this is a really easy problem, you can see it, you can tell there is a balcony, there is sea view and all that. But how do we make sure that our machines are able to learn that and detect that in any new image that comes up? So while this is a hard problem to solve, this is an interesting one as well, because the context matters a lot. What I mean by that is, if we pass this image to some existing models that are there by Google or by Amazon, these are the results we get. We get like oceanfront, nature. It tells us it's a building, apartment. OK, it's an apartment, but what do we do with it? It's not that these models are not good. These are really good at predicting what they see in this image. But in our context, there are different things that matter for us, like sea view. We care about if there is a sea view from a particular room or not. We care about if there is a balcony, if there is a bed, if it's a bed photo, or if it's a seating area or not. And before you start thinking it might be OK, it might be an easy problem to solve, there are a couple of challenges with that. First of all, it's not an image classification problem, which means there are going to be multiple tags for every image. So it's not like you just classify it among the categories that you have. There are going to be different things, different tags, multiple tags for one image. And another challenging part is there is going to be some sort of hierarchy of these tags. Because if you know that this image is of a bed, you can say that this is an inside view of a room. unless you're in such a room where there's no room, only the bed. So once we know what's there in an image, we can use that information to help our customers in making the decision about the property they want to book easier and faster. Another application that we saw at Booking was recommendation engine. And the problem is really trivial. User X booked a hotel Y. Now we have a new user, Z, and we want to predict what hotel are they going to book. Or in general, what hotel are they more likely to book. So the objective of this problem here is find the probability of booking a particular hotel by a particular user. So as you can already guess, there are some features that we have, like user features, which are about the particular user. Where are they from? What language are they browsing in? Then there are some contextual features, like what's the day of the week? When are they looking for it? What's the season? Where are they from, depending on the localization? And then we have some item features, which mean the properties of a particular hotel, like what's the price, what's the location, what's there in the neighborhood, and all that stuff. So the research has shown that if you use deep learning, build deep models with a lot of features, it becomes better to recommend a hotel to a user as compared to the collaborative filtering, which is a non-deep learning way of doing it. So once we saw there were some applications where we could utilize deep learning because we had a lot of data, we had a lot of context, a lot of features about both the properties as well as the users, we started exploring deep learning, and credit goes to my colleagues, Stas and Imra, who started exploration of deep learning. And these days, we actually have a lot of models which are working on deep learning, on the base of deep learning, and they are in production these days. So next, let's talk about the life cycle of a model. This was about what are the different areas where we explore deep learning, and now let's talk about what exactly a model is and what are the different phases. So there are 3 different phases. One is code, then we go to train, and then deploy. In first stage, data scientist is responsible for writing the model, writing the code for the model. And you may be using any kind of framework available or library available. We use TensorFlow Python API to write our models. And in this stage, data scientist tries out different kind of features, different kind of embeddings, different kind of architecture of the model, and try out things on the sample data. And once they're happy with their model, and once they're happy with all the stuff they have been doing, and once they're happy with the accuracy that they get on the small data, now is the time to actually train the model on a bigger data, on actual production data, so that we have a good model which learns a lot of stuff and is able to predict accurately. That's the train part of the life cycle. The next, once we have trained the data, trained the model using the production data, we go to the deployment stage. And these 2 parts, training and deployment, these are the 2 parts which build up the production pipeline that I've been talking about, and that we'll see in detail next. So for those who have worked with machine learning might argue that training, why do we need training in the production pipeline? We can also train our models on laptop, right? But if you try to do that, if you try to train your model on your laptop, this is what you may end up looking like. So there are a bunch of different reasons why that's the case. One is the lack of resources on your machines. It's possible that you don't really have enough number of cores or enough GPU to be able to run the training at a good speed on your laptop. And another thing is your production data may be too large to be able to read in memory. So this is why we train our models on our servers, which have high resources and not really on the local machine. So this is how it looks like, the training of a model in production. We have our training script. We have our big servers, which have a lot of resources, and we run those training scripts on these servers. Easy, right? You just replace your laptop with a bigger server, and that's it. But there are problems with this approach as well, because now there are going to be multiple data scientists who are going to be running their trainings at the same time. Yeah. So there are going to be multiple data scientists which are going to be running the model trainings at the same time. We are not going to be able to provide them independent environment. We are not going to be able to provide them support for different versions of the libraries. And yeah, this is how I'm going to move to the containers. So this is what we do. We have our training script. We wrap them up inside a container. So now what is a container? Container is a lightweight software package which includes all the dependencies that your software needs to run. So every time we want to run a training of a model, we take the training script, we package all the dependencies that we want, that our training needs, and wrap it up in a container, run that container on our servers, on one of our servers. So this way, these containers are also able to use the GPU support that is available on these servers. So we can directly link up some of these containers with the GPUs that we have available on our servers and run the training faster than running on your laptop. So this is how it looks like. We have our production data in Hadoop storage. Every time we want to train a model, we spawn up a new container which has the training script with all the dependencies that it requires. It takes the data, production data from the Hadoop storage. It runs the training. It does all the computations, all the training on that data that it gets. And once the training is done, we want to make sure that it's able to store back the model checkpoints that has been trained. So model checkpoints are like model weights, which the model has learned after all the training process. So model checkpoints is a term that's used by TensorFlow to denote these weights of these parameters of a model. And once it's done with the training and it stores the model checkpoints back to Hadoop storage, the container goes away. Exactly. So who can be more selfless than a container that it takes birth to do the stuff that you want to do and then it dies? So once we are done with the training, we now have the model that has been trained on the production data. We had exported its checkpoints. The next step is to be able to deploy this model so that we can actually serve these predictions from this model to our clients. So let's talk about how deploying of a model looks like. We have a Python app which runs in a container again, in a container because we want to make sure that all of our different models are running in different specific environments for the same reasons as having different versions of the dependencies. Then it takes the model weights from the Hadoop storage, which we stored in the previous step, and loads the model in memory. So to load a model, a trained model in memory, we need two things. We need the model definition. That means all the features, all the interactions of our features, all the information about what our model looks like, the architecture of the model. And the next thing we need is the model weights for particular parameters that we trained in the previous step while training the model. We combine these two, and we have the model ready in memory to be able to serve the predictions. And on the top of that, it provides a really nice URL to get predictions. And so this is how it looks like. We have an app running, does the same stuff that I mentioned just in the last slide. It is able to serve predictions using this mechanism. So client just has to send a GET request with all the input features and get back the response, which contains the which contains the prediction which you are expecting from that particular model. But since we work at large scale, our problems don't end up with just having one server. We have multiple. We can create multiple replicas of those containers serving the app, and we put them behind a load balancer. Now, client is it doesn't really care about how many apps we have running, and it's just sending the request to the load balancer API, and load balancer is responsible for distributing the traffic so that we are able to serve more requests per second. But as we have large scale, problems get bigger. We have more and more number of containers for a particular app. And at some point, when you keep on increasing the number of containers, you need to find a way to manage these containers, because it's really difficult if you have all this cluster of these containers running somewhere and you don't really have a way to manage them properly. So we use Kubernetes for that. Kubernetes is an open source project by Google. They handed it over to CNCF, Cloud Native Foundation. And Kubernetes is a container orchestration platform which helps us in scheduling, managing, creating, and doing all kind of stuff with the cluster of containers. So now, Kubernetes handles all the pain of managing the containers, maintaining the number of replicas in a cluster. For example, if we want to make sure that we always have like 50 containers for a particular app, we just specify that in the configuration. And Kubernetes is going to make sure that if some of the containers are dying because of some error, because of some network issue or something, it's going to make sure it creates more containers, more replicas of the same type, of the same specification that we mentioned, and maintains the number of replicas to a particular number that you mentioned. And it's also really easy to scale up or scale down based on some parameters. Like, for example, you want to scale up when you have a lot of requests. And how do you measure a lot of requests? It may be like you check the size of your WSGI queue. You may check the CPU usage on your apps, and once it crosses the threshold, you may want to increase the number of replicas that you have. And Kubernetes provides a really nice API to do all of that. So once we have deployed our model, what's next? Since I mentioned we work at a large scale, the problems don't really end up with putting the software in production. There are problems with the performance measurement, and how do we measure the performance of a model that's in production? So let's say you have a model and it takes some computation time to compute the predictions for a given set of input features. But that's not going to be the time that your client sees. There's going to be some request overhead. So let's say you have some request overhead, and your total time is going to be request overhead added to the computation time that it requires for all the predictions that you want in one request. As we can see, if we have some really simple model, like a model with less number of input features, less number of interactions, and or maybe less number of hidden layers or neurons, we are going to see that the request overhead is going to be the main bottleneck of serving, because the computation time is going to be really small because there is going to be less computation, and of course going to take less time. And in those cases, request overhead is going to be the main bottleneck for you to be able to optimize your serving. So once we know what does the performance look like, what the prediction time look like, we can try to optimize for our use case. And we can try to optimize either for latency or throughput. Let's talk about both of these one by one. So optimizing for latency. Latency is the amount of time it takes for one request to return the response to the client. So you may want to optimize for latency when you are serving some prediction in real time. For example, if you are serving something on your website, in your app, when you really want to make sure that the prediction is back by the time you're showing something to your users. So the first thing that you can do for optimizing for latency is do not predict at real time if you can pre-compute. This may look funny in the first time when you'd say, okay, we are actually trying to predict in real time, but you're saying you don't predict, because the latency is going to be always better if you don't do anything in real time. So the point behind this is that sometimes when you have a limited set of features, it's possible that you are able to pre-compute all the results and able to store the results in a lookup table for all the set of different features that you may have. And so using this information, now you can serve your traffic, serve your predictions faster than you would do if you were computing the predictions real time. Another thing you can do is reduce the request overhead. When you know that request overhead is the main bottleneck for your serving, as we saw in the last on the last slide, you may want to reduce the request overhead. And one of the things that we do for reducing this is making sure that we reduce the latency between the app getting the request and being able to predict. So basically what we do is we get the model right into the memory of the app. So it's embedded right there in the memory, and once the app gets the GET request, it's able to forward those input features directly to the app and get predictions back. So we reduce the request overhead by embedding the model right into the app. There might be other ways to solve this as well. Next thing is always predict for one instance. And that means if you have, let's say you want to predict for 3 or 4 different set of input features, and you want to optimize for latency, it's better that you have only one feature request in every request you make. So you have one row of features, one input features for your one request, because this way you're going to get the predictions as fast as possible. And then there are some other things like quantization. You may want to lower down the precision value of your input features from, let's say, float 32 to fixed 8-bit value. And how that helps is now you're able to store 4 times more data in your processor. And that means your CPU is now going to be able to compute things faster. So that means you serve your predictions faster than before. And since we use TensorFlow, there are some TensorFlow-specific techniques like freezing the network. That means you change all the variables to constants. So that helps you a little bit in the computation time. And the next thing is you optimize for inference, which means you remove all the nodes that are not used in the prediction time, and hence you make the computation faster. Now the other use case is optimizing the serving for throughput. So throughput is the amount of work you get done in a particular unit time, or some particular time. Now, you may want to optimize for throughput when you care about how much work is getting done, or how quickly is a batch of work getting done. Like if you have some cron job which runs every day or even every hour, all you care about is when is all the work getting done. You don't really care about when is one prediction there for you. So you may want to optimize for throughput to make sure that you're getting done the work that you want to do quicker. Again, the first thing is do not predict real time if you can pre-compute, as I discussed earlier. The next thing is batch the request. If you have a lot of requests, a lot of features that you want to predict on, always batch your requests so that, for example, if you batch your request to send 10,000 requests with one HTTP request, now you're going to reduce the request overhead for all of those requests which were going to be there if you were sending one by one. This is what we actually use a lot to get our work done when we have a lot of work to be done in cron job or Uzi workflows. And another thing is parallelize your request. Don't wait for one request to be complete. Do the request asynchronously so that you can get a lot of work done quickly. So now I will try to summarize the things that we talked about so that you actually take a whole picture of what we talked about and how we do stuff, because it was, I think, a lot of different kind of things. So first of all, we talked about training models in containers. Every time we want to train a model, we create a new container. It has the training script and all the dependencies, get the data from Hadoop storage, run the training. Once the training is done, save the model checkpoints to the Hadoop storage back, and that's it. The container dies. It's so selfless. Once we have the model weights ready, once we have done the training, the next step is to put the models in production. And for that, we have a Python app which loads the model in memory using the model definition and the model weights that we collected in the training, creates those containers as part of the clusters that are run by Kubernetes, because Kubernetes helps a lot with the managing all the different clusters of containers for particular specifications. And the next is optimizing our serving for different use cases. If you have a real-time use case, you may want to optimize for latency. And if you have a use case where you want to do a lot of work in one burst, it's better to optimize for throughput. And I've mentioned some of the techniques that we can use to optimize for both of these use cases. And if you want to get in touch with me, I'm available on social media, almost all of them. All of these, I am Sahil Dua 2305 on most of them. And yeah, that's it. Thank you.